Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Pedro Cunha. He did his PhD in 2019 at Lisbon East and is currently a long-term research fellow at the University of Aveiro at the Department of Mathematics. Thank you, Pedro, for agreeing to give this talk. The stage is yours.
Thank you very much. Hi everyone. Thank you, Torben, for the very kind introduction and also for the very kind invitation to deliver a talk on this seminar series on gravity and cosmology, if my understanding is correct. So in this seminar, I will focus mainly in one of my recent papers that was published fairly recently in the Journal of Cosmology and Astroparticle Physics. But I will also mention some other works, namely with other collaborators, mainly in the group in Aveiro. But I will also mention some other works from other people, just to kind of motivate the discussion. So any comments and feedback would of course be most welcome. But if you prefer, feel free to send me an email after the talk. You can find my email in this slide, and feel free to send me an email. So we can begin with an overall question and also a problem, which is trying to understand the true nature of astrophysical black holes. So the question is, are they all described by the celebrated Kerr metric? This question comes within the context of the Kerr paradigm, which essentially assumes that essentially all black holes that exist in our universe are described by the Kerr solution, regardless of the formation mechanism. And essentially, this Kerr paradigm is partially motivated by the so-called uniqueness theorems. Is a set of very famous theorems that were developed mainly in the 60s and 70s, namely by Israel, Carter, and Robinson. And these theorems essentially state that if you have an equilibrium black hole in the vacuum of general relativity with a regular metric on and outside the horizon and asymptotic flatness, then Kerr is the only solution. Not just one solution, is the only solution. So are astrophysical black holes then really described by the Kerr metric? Well, I guess the answer to this very important question depends if the assumptions of these uniqueness theorems are satisfied in realistic conditions. And it turns out that by violating some of the assumptions of these theorems, you can get very different solutions. So could it be possible that astrophysical black holes could be perhaps better described by some other black hole solution, but instead of vacuum, something outside vacuum with matter fields, or perhaps in a theory beyond general relativity, so it's not GR? Or perhaps, a very intriguing question, perhaps could these astrophysical objects be described instead by an ultracompact object that doesn't have any horizon, so it's not a black hole, but it is something else that just happens to mimic a black hole? So the seminar will focus mainly on this last possibility, the possible existence of a black hole mimicker. But before we go into that direction, let us just briefly review some results on black holes. That will be important for the discussion later. So it is fairly well known for this audience, I think, that strong enough gravitational fields can bend the trajectory of light rays and even close them into a circular orbit called light rings. So in this context, a light ring is a circular orbit of null geodesics that are closed when the orbit is projected into 3 spatial dimensions. It is a fairly common knowledge that Kerr black holes have a light ring around each black hole, one light ring for each rotating sense. But a very interesting question is, okay, so we know that Kerr has at least one light ring, but do all black holes need to have a light ring around them? It's a much broader question. It turns out that it is possible to show generic existence results of light rings using topological arguments. So in a paper published that I've published together with Carlos Herdeiro, we have shown that any stationary and axial-symmetric and asymptotically flat spacetime that contains a black hole that is non-extremal, that is topologically spherical, and with a killing horizon, admits at least one standard light ring, standard meaning that it's of the Kerr type, outside the horizon, and this for each rotating sense. So as a technicality, let me just say that the result assumes some smoothness of the metric and also circularity, which essentially boils down that the geometry looks the same if we reverse both time and the direction of the black hole rotation. But essentially does not involve the field equations. So it's the main core of the argument is topological. The key point that I'm trying to make is that light rings are indeed a generic feature of black holes under very reasonable and generic conditions. And what's interesting is that these light ring orbits are critical for several astrophysical observational targets. One of the best examples is the edge of a black hole shadow image, which is determined by light rings, and also some generalizations of these orbits. For example, the famous image of M87 star by the Event Horizon Telescope is consistent with the prediction of general relativity of a Kerr black hole image with a shadow. Since this is important to understand the role of light rings and the connection to observation, let me expand a little bit more on this so we can better understand the relation between black hole imaging and these light ring orbits. I'm just now make a very brief short detour from the main discussion. So consider for the moment a very academic scenario as follows. You have a person that is looking at a black hole, and far away you have stars in the background behind the black hole that will provide light to provide contrast to an image. If you want to simulate an image, this can be done via backwards ray tracing, which is kind of depicted in this drawing here. You have light that is received by each pixel in the image, which is integrated backwards in time from the location of the observer backwards in time, and you try to see the origin of each light ray. If, for example, a given light ray reaches a faraway star, then the observer pixel, that specific pixel, then it gets some light from that specific star. But if the light ray, when propagated backwards in time, falls into the black hole, then it means that no light came from that direction and the pixel is black, essentially. This process is illustrated in this video that I'm showing here, in this animation, with the light rays in blue with the light rays are shown in blue around a Kerr black hole, and in red is a Kerr black hole. In the red sphere is a Kerr black hole. So this process can be used to numerically simulate the optical image of a black hole, which is, I'm depicting it in the top right corner of this slide. And this is the same image, but amplified, so you can see better. You can see how the strong gravitational lensing deforms the star field in the background. And the key point is that in the center, we have a large dark region, and which is called the black hole shadow. And that shadow is the actual image of the black hole. It's fairly easy to understand that since the black hole does not emit light, at least classically, then the shadow is essentially the absence of light, and that makes the name shadow quite appropriate, because shadow is literally the absence of light. We can understand the relation between the shadow size and the light ring better if we think about in terms of a scattering process. So I'm making this drawing here of a black hole, which is the black circle. And around it, there is a light ring orbit, which is the dashed circle around it. If we make a scattering of a light ray close to the black hole during the ray tracing process, but with an impact parameter that is large enough, then the light ray is able to escape the black hole after it reaches a minimal distance. But if we choose instead an impact parameter that is too small, then the light ray falls into the black hole. And this would lead to a black pixel that would be part of the shadow. But if the impact parameter is just right, the gravitational field of the black hole will bend the light ray enough such that it closes over itself. And in this limit, the light ray approaches this limit orbit, which is precisely this light ring I've been mentioning. So, of course, in a more realistic scenario, the light source that gives contrast to an image of an astrophysical black hole does not come from a faraway star field, that as I have represented here, but instead from radiation from an accretion disk flow close to the black hole. But nonetheless, the shadow image, or at least the edge of the shadow, still appears as a sharp feature in the image. This is kind of depicted in these two images here that you can see. The edge, this sharp ring, corresponds very approximately to the edge of the shadow. This was obtained by the HT collaboration, or people involved in the HT collaboration, if I recall correctly, and using GRMHD. And then if you apply a Gaussian blur, you get something very similar to what actually the HT observes. So the key point is that light rings, which determine part of the shadow edge, are directly connected to astrophysical observations. That is the point I'm trying to make here. Okay, so with that out of the way, let's consider black hole mimickers. So what if astrophysical black holes are actually not true black holes? Perhaps they might be something else that has a light ring orbit, which just makes them look like they are a black hole. So this is a fairly intriguing possibility, and it's an open research problem, and this is something that I would like to consider for the rest of this talk. So let's consider, by assumption, that astrophysical black holes are actually horizonless objects that are very compact, but that are stationary, axially symmetric, and in an asymptotically flat spacetime. If the object is compact enough, then the gravitational field can bend, again, the trajectory of light rays enough to close them into a light ring. So, although light rings exist around black holes, they can also exist for objects that are very compact but that do not have an horizon. So, and in a very similar way, they can also play a part in the image formation as well. But now there is a key difference with respect to the black holes. So you may recall that for a black hole, a single light ring can exist in each rotating direction. But now, and in contrast to black holes, in an horizonless compact object, light rings must appear in pairs of two. This again follows from some topological results. You can check this paper that I have published together with Emanuele Berti and Carlos Herdeiro. And essentially the result is that one of the light rings is of the standard type, in the sense that it's of the same type that exists around a Kerr black hole. And because of this, the standard light ring could potentially allow this horizonless object to mimic some features of a black hole, even without having an horizon. But the second light ring, it is of an exotic type. And it turns out that if the null energy condition is satisfied, this light ring, this exotic light ring, must necessarily lead to a stable trapping of null geodesics in its neighborhood. The critical thing is that the presence of an exotic light ring has been suspected to trigger an instability in the object. It's still an open problem, but has been suspected to trigger such an instability. So, if such an instability is generic, then this could be a problem for the viability of these kind of horizonless theoretical alternatives to black holes. So this is a problem worth exploring. So for the rest of the talk, I will briefly review some of the results in the literature that provide an indication that exotic light rings might cause an instability, although, like I have said, this is still an open problem. First, there is a paper published that I've published together with Carlos Herdeiro, Jean Radu, and Nico Sanchez-Gual that performed full numerical evolutions of compact stars in concrete models. And we observed that stars became unstable when the light rings were present. Then I would like to mention a paper by Kier that shows that an exotic light ring leads to a slow decay rate for the linear wave equation. It's an analysis that can be informative of the potential nonlinear instability of the star using some conventional methods. Next, I will mention a recent paper by Benomio, Avendano, Pretorius, and Sullivan that showcases how the presence of an exotic light ring can create unbounded growth of higher derivatives in a cubic nonlinear equation. So this equation is just used as a proxy for gravitational perturbations. And let me also mention that similar results were also reported in a follow-up paper by Redondo and Avendano. Finally, I will then talk about my recent paper in JCAP, which attempts to make a contribution to this discussion. So this will essentially be the plan for the talk. Let me now go point by point and so say a few words to give some context. So in this first paper, we have performed a full 3+1 dynamical evolution of the field equations in concrete models. The first model was complex Proca, which is just a mass term and no self-interactions. And initial solutions that were evolved, so the initial solution at t equals 0 were rotating mini Proca stars. They are equilibrium solutions that might be stable or unstable, but they are equilibrium solutions. The second model has a complex scalar with a solitonic type of interaction potential. And the initial solutions, in this case, were rotating solitonic boson stars. Both of these models, so both model 1 and 2, they are horizonless compact objects that can possess light ring orbits when they are compact enough, so in some regions of the solution space, and they can appear in a well-defined physics model. So they have a well-defined Lagrangian. So starting with model 1, this diagram is a diagram of the family of solutions of mini Proca stars as a function of the total mass and harmonic frequency omega of the Proca field. The solutions that have light rings, they exist to the left of the pink asterisk. So essentially, to the right of the light ring, you get solutions that are more diluted, less compact, and you can see as omega tends to 1, the mass goes to 0. The solution becomes very diluted, and you reach this kind of Newtonian limit. So as you go up the red curve, which each point is a different solution, you will get essentially a more and more compact configuration, naively speaking. And after you pass this pink asterisk, you get a light ring pair formation, and you get both an unstable or standard light ring and also an exotic light ring. So then what we observed, we made simulations of several solutions, and what was observed was that solutions without a light ring were stable within the numerical time of the simulation. And in contrast, solutions that were compact enough to have a pair of light rings, they showed an instability. So, of course, there could be several end states for the instability. For this specific model, the endpoint of the instability was a migration to a solution without light rings. So in this case, the solutions adapted during the time evolution. It's a full 3+1 numerical evolution, and then they attempted to destroy their light ring structure. For model 2, the picture is very similar. Solutions that had light rings were observed to be unstable, and the main difference was that the endpoint of the instability. In this case, the model collapsed into a black hole. So Let me just make a couple of extra remarks. First, the observed instability was consistent, even if you use different gauge choices and different numerical schemes. There's actually a paper with extra details on this that is currently in preparation. Let me also emphasize that the instability that we observed had no other obvious source other than the presence of the light rings, because in principle you could expect instabilities to occur due to other factors. There was no other obvious source other than the presence of the light rings to produce this instability that we observed in this case. And let me also say that the instability appeared to excite non-axially symmetric modes. So this last point is relevant because it appears that forcing an evolution with axial symmetry appears to essentially kills this instability. So the absence of an instability in simulations, for example, reported by Simonsen in his paper, for a very similar model are consistent with this point. Moving now to the second point of the talk is the linear wave equation. So we can consider the dynamics here of just a linear wave on top of a fixed spherically symmetric spacetime. So the space-time is fixed, is not dynamical in this case, and you try to analyze the dynamics of just a test field, scalar field, that satisfies a linear wave equation. So for this system, it's possible to define a first-order energy of the linear wave, which is essentially an integral over space at a constant time of a positive measure, which is essentially a sum of square terms. And it's this kind of capital F function that I'm defining here. So this measure only depends on derivatives of the field up to first order. So that's why it's called the first order energy. You can also, in a very similar way, define higher order energies, a measure for higher order energies, which contain higher order derivatives. But the expression is very similar to the one above. If you want, at the end, I can show you the explicit expression. Is not too illuminating, I'm afraid. But what matters is that you can have an integral at a constant time with a sum of square terms, so it's positive defined, with derivatives only up to kth order. And it turns out that a solution to the linear wave satisfies the following properties. First, there is a conservation of the first order energy. And higher order energies are bounded from above. And also that the energy measure has a local logarithmic uniform decay rate. So let me boil down what this means exactly. The fact that it's local, it means that this relation is defined on a local region D around the exotic light ring. Okay? The logarithmic decay is, in this case, actually connected with the existence of stable null trapping around the exotic light ring. The word uniform is also very important here. So in this context, used by the Kerr author, it means that it holds this condition. It holds for any solution to the wave equation for all times. So to help visualize this, let's draw a line with a growing decay rate. And individual angular modes can have a very fast decay rate, usually exponential. And by comparison, this log decay that I'm mentioning is very slow. And if there is stable trapping, the uniform rate, which is, remember, valid for any solution, must be of this type. And actually, this sort of log decay is actually the fastest possible uniform rate that can happen if there is stable trapping. So these are results in spherical symmetry, just to emphasize that. So if instead of an exotic light ring, if we had a standard light ring, like in Kerr, for example, we have something slightly different. Instead of a polynomial decay, you would have instead of a log decay, we'd have a polynomial decay as the fastest uniform decay rate. So the difference is that this polynomial decay rate is usually enough to prove nonlinear stability of the spacetime. But logarithm decay is not enough to prove nonlinear stability, at least using usual methods. So in this case, the spacetime with an exotic light ring might be stable or unstable. We cannot be for sure. We cannot know for sure. So this alone, of course, does not prove that spacetime with an exotic light ring will develop an instability, but quoting Pierre, it can be highly suggestive that such an instability might appear. So the third point of this talk is the cubic nonlinear wave equation. So it's not just linear wave, it now has a source term, or a cubic source term. So in this paper, the authors have solved numerically a nonlinear wave equation on the background of a fixed four-dimensional static and spherically symmetric and asymptotically flat spacetime. The metric has this very simple form, and the function f is just an ad hoc function that, as far as I could understand, is not very well. They have not properly motivated it, but the key point is that it has two light rings. And so the geodesic motion is determined essentially by an effective potential H, which is plotted in this figure. So I'm not giving too much details, but the minimum of this effective potential is the stable light ring, which in this case is an exotic light ring, and the maximum, local maximum of the potential is just the standard curl-like light ring. Again, let me emphasize that the spacetime itself is not made dynamical. The spacetime is fixed. What the authors do is that they solve numerically this cubic nonlinear wave equation for a real scalar field on top of this spacetime. And the motivation to consider this nonlinear wave equation is a simple proxy for gravitational perturbations, as they state in their paper. So in this case, again, we can define a first-order energy measure for the scalar field in a similar fashion to the linear equation. And again, this quantity is also conserved over time, but we don't have a similar conservation or a similar bound on higher order energies. So this implies that there must exist a bound on first derivatives of the field, but this can still be compatible with an unbounded growth of higher order derivatives. So higher order derivatives can grow without bound. In principle, it's not forbidden for this equation. And actually, this is precisely what was observed by the authors. So these two plots show second order derivatives growing on average over time. And something very similar happens for higher order derivatives. And this growth happens in the neighborhood of an exotic light ring, of the exotic light ring. And so to illustrate this, this is a plot of the time evolution of the test scalar field done by the authors and represented over the spatial Cartesian spatial coordinates. So this frame is for the initial time, with the initial lump that you see close to the exotic light ring. And as time progresses, there is some dispersion of the field, but a high frequency component remains at the initial location. And at later times, part of the solution with a high frequency remains confined in the stable trapping region, close to the exotic light ring. So just to stress that this growth is tied to a nonlinear phenomena, the authors have compared also higher order derivatives, namely the second order derivatives in this case, to the nonlinear equation, and then compared with the linear wave equation for the same initial data and setup. And as you can see, where you see a growth, an average growth for the nonlinear equation, for the linear equation, you see a decay. So the point is that this growth cannot be probed at the linear level. This is the point that they try to make. The authors also very nicely show that a sort of energy cascade is taking place. So to do this, they define some Fourier coefficients with a certain L mode of the scalar field at the exotic light ring radius at a given fixed time coordinate. And the authors then analyze how these coefficients of the nonlinear wave equation change over time. So this is a plot of the L spectrum of coefficients at initial time. In gray here is the numerical floor, so data is zero essentially in this region within numerical precision. I hope you can see in your screens this gray region. It's a little bit harder to see now that I'm
It's
seeing, but
visible.
it's visible. Okay, great, thanks. In this specific case, the initial data for the scalar field had only the L equals 1 and L equals 2 angular modes. And if you evolve slightly over a small period of time, this is the L spectrum after making this small time evolution. Just a few words about this. The authors saw the formation of a ladder or these kind of steps, with each step having approximately the same width. And each step, which has approximately the same amplitude, corresponds to a generation. That's what they call. And here I represented the first, second, and third generation. And this essentially corresponds to an energy cascade, with energy being transferred from one generation to the next. And as discussed by the authors, the size of the first generation is essentially due to the cubic power of the nonlinear equation that is being evolved. And as time progresses further, you can see that let me go back. You can see that the spectrum curve approaches essentially a stationary regime. And in short, the high frequency modes dominate at late times. Now, recall that since the total energy measure is conserved, then there must be an energy transfer from low to high frequencies. So, just a couple of extra remarks about this paper. The growth of these higher order derivatives was connected essentially with the exotic light ring, and there is a cascade mechanism that transfers energy from lower to higher modes. And since the total energy is conserved, then one can expect the back reaction on the spacetime to be limited, even though there are higher order derivatives that are growing locally, virtually without bound. Now, going a little bit beyond this paper, I would like to make the following points. This is my personal perspective, of course. And I would very much like to hear your opinions about that. You are free to send me an email. First, I think the energy conservation for this equation is a very specific feature. If there was no conserved first-order energy, I would say it would be reasonable that the energy would also grow unbounded via a similar mechanism, and would also start to back react on the spacetime. And this is something that we can naively expect from a proxy for a nonlinear gravitational perturbation, that before a back reaction is taken into account, it would appear non-conservative. So, assuming that to be the case, what could be the result of a back reaction of energy trapped around the exotic light ring? Would it destroy it? Make it more efficient? So that is the question that I will now attempt to address as I now move on to the last point of the seminar plan. So to address the problem, we are going to consider a continuum-shell star as a toy model. So this is essentially a static, spherically symmetric, horizonless spacetime that is asymptotically flat. The metric only depends on a single function, which is this mass function m of r, just a single function. The metric describes the space-time continuum limit of having multiple thin matter shells that are very close to each other, and you make this into the continuum, and with each matter shell supported only by tangential pressures and with vacuum in between the shells. You can see the details for this claim in the paper. But essentially, the energy momentum tensor takes a very simple form in this space-time, and the radial pressure vanishes identically. Actually, you could have started the other way around. You could have started with a generic static and spherical symmetric space-time with no horizon, and then postulate that radial pressure is zero, and you get essentially the same thing. But uh, it has this also very nice interpretation of being you can build this out of multi-layered shells with vacuum in between and only supported by tangential pressures. So this is essentially the expected behavior from this construction of multiple thin shells, which are not supported by any radial pressure. So, given some mass function, the tangential pressures adapt to kind of provide support against gravitational collapse. And as a side note, it's possible to show that these stars always satisfy the weak energy condition, provided that the mass and energy density are positive and that the star is horizonless. The light rings, which are closed orbits of null geodesics, can be obtained in this space-time by the zeros of this function C of R. You can kind of notice that if this was Schwarzschild, then the mass function would be essentially outside the horizon would be a constant, and this light ring condition would tell you that there is a zero when R is equal to 3m, which it's kind of a result that might be familiar to you, that light ring is at that location in Schwarzschild. But this is just to make that connection. This is for an horizonless star, not a black hole. So for an horizonless star, this is a typical plot of this function C. If you enforce regularity close to the center of the spacetime and also asymptotic flatness, this essentially constrains the scaling behavior at the endpoints. And so if there are zeros present, which will be the light rings, then they must appear in pairs. Essentially, this is kind of recovering the statement that I made earlier on, that for an horizonless stars, these light rings must appear in pairs, but that statement also holds true beyond spherical symmetry. Spherical symmetry, it's almost obvious. So the innermost light ring in this case is exotic, is the stable light ring, and the outermost light ring is the standard Kerr-like light ring, which is unstable. So what happens? Now you can ask, what happens to the locations of the light rings when there is an accumulation of extra energy around the exotic light ring? What happens? So what we are going to do is consider a static and also a spherically symmetric perturbation. We are going to assume that the perturbation is due only to additional energy close to the exotic light ring, okay? So this is a kind of a key assumption here, that the star is made of a very stiff material and the star layers do not actually change position under the perturbation. It's a very artificial assumption, but it allows us to focus only on pure effects from the back reaction of energy around the exotic light ring. So essentially what happens is that this perturbation creates a shift in the light ring radius with respect to its unperturbed location. And the new light ring location must also satisfy the light ring condition. So it must be a root of this C function at the new light ring radius. If we now take this expression and if we expand this relation for very small perturbations, we obtain a very simple relation for the variation of the light ring location under a static perturbation. And if we assume that this mass perturbation is always positive, which is kind of reasonable since it comes from this kind of extra energy at the stable light ring, then the sign of this ratio that I'm showing here will depend only on the sign of the derivative of the function C at the light ring location. So if we now look at the typical plot for the C function, a simple inspection tells you that the innermost, which is the exotic light ring, will shift inwards under the perturbation, and the outermost, light ring, which is the standard one, will be shifted outwards because the derivatives have different signs. We can then conclude that we expect these light rings to be pushed apart as a consequence of the back reaction of the extra energy at the exotic light ring. We can now also ask a very similar question for the effective potential H, which essentially determines the trapping capacity of null geodesics around the exotic light ring. So, under the perturbation, what is the change of the potential shape at the exotic light ring? It turns out, if you do the computations, that the variation of the potential at the exotic light ring for very small perturbations boils down to the product of these two positive terms with a minus sign in front. So essentially this implies that the potential becomes deeper as the exotic light ring, and so the stable trapping appears to become more efficient. So now with these results, which are kind of at a linear level, you can look at some nonlinear perturbations and then look at a very specific case to understand better what's going on. So let's consider a very specific mass function profile for the unperturbed star that you can see here and the corresponding mass density. This profile is somewhat arbitrary, but it has the advantage of allowing several calculations to be done analytically, even in this nonlinear regime, so which is nice. And so for the perturbation, we are going to consider two different models. In the first model, we can approximate the extra energy density around the exotic light ring as a Dirac delta distribution, which is centered at the exotic light ring location. So this is it's a toy model, of course. And in this case, the mass function simply becomes a step function. This static perturbation introduces a mass scale mu, which is not necessarily small in this case. In the second model, the energy density distribution is kind of more spread out. It's kind of a Gaussian profile, and it's centered around the exotic light ring. And the factor A that we have here for the density essentially is calculated to normalize the mass scale of the perturbation to be mu. So the main advantage of the perturbative model 1 is that all calculations can be done analytically. And you can check the full results in the paper if you want. Model 2 is a bit more realistic, but it requires numerical methods to analyze. So that's the trade-off. So if you do the calculations, and these are the plots that you obtain for the effective potential H for different values of the perturbation mass scale mu. Lines with mu equals 0 is essentially the unperturbed potential, so it's potential without a perturbation. And you can see that increasing the perturbation, the mass scale of the perturbation, makes the light ring drift away from each other, which is something that we have anticipated in the previous discussion, but at linear level. We can also see the potential becoming deeper around the exotic light ring as mu increases, which is again also expected, but from the linear analysis. And the plots from both models are very similar, although if you look carefully, they are slightly different. And actually, this shows that the analytical model, which has a Dirac delta, captures very important features of a more complicated case with a kind of a Gaussian distribution of the perturbation. And in some sense, it makes sense because as the Gaussian width goes to 0 in case 2, you can recover case 1. And this was done also as a sanity check. So let me end with some final remarks. So the conclusion from this analysis is that the pure effect from the back reaction of a lump of energy around the exotic light ring is to make the trapping more efficient, since the potential well becomes deeper. So this could potentially further amplify the instability if it exists. So the conclusion remains essentially So as discussed in the paper, although I have not given details here, the conclusion remains essentially the same if we take stars that have a non-zero radial pressure. Okay. But these require further assumptions, but I would say they are reasonable, but they do require further assumptions. So further work is nonetheless necessary to see if we allow the star to restructure itself under the perturbation changes this picture. If you recall, I mentioned this is a critical assumption. But nonetheless, we can expect the basic mechanism to remain the same. So with that, let me close with some open questions, namely that there is still a lot of details about this light ring instability that are not yet clear, namely how general it is, if it can be quenched in some models, if it's linear or non-linear, how can we predict the timescale of the instability. These are, as far as I understand, open problems. And solving these questions will be hard, but I would say it is necessary if you want to clarify if this very broad class of horizonless ultracompact objects can be viable black hole alternatives or not. So with that, thank you very much, and I will cede the stage.
Very much, Pedro, for the really nice talk. Are there any questions? The chair.
Yeah, thank you, Pedro, for the very nice talk. Yeah, actually, precisely have the question about the time scale. I'm quite interested in in the community, do people already know through maybe numerical nonlinear analysis which kind of factor controls the time scale, roughly speaking?
So this, as I said, this is an open problem. The problem is that you could expect some important physical property of the stars to control the time scale. It's not entirely clear what is that, if what would be the relevant physical time scale, because there are different time scales that could be involved. For example, for a star, you have the orbital the orbital frequency at the stable light ring. You have the radial oscillation frequency around the light ring. You have the light crossing time of the light ring. So there are plenty of different physical timescales, and they could probably play with each other in a very non-clear way. We actually tried to play around with some of these scales, and it's well, of course, there is some connection, but there was not a very clear picture, at least at this moment. The fact this problem is intrinsically non-linear, we observe this instability growing in non-linear evolutions. It makes it harder to kind of understand analytically what's happening. It's not very clear at the moment how to predict this time scale. For example, for the particular boson stars and Broca stars that I mentioned, that the time scale of the instability was around 10 to the 3 m, more or less. So a few thousand light crossing times, more or less. So it's not that large. But is that time scales very specific of these models that we don't have statistics. It's very unclear. So I'm afraid I don't have a very good answer to you.
No, it's okay. Because recently my colleagues and I, we are working on a model which is also a horizonless compact objects, but it has a very strong redshifts in the sense that I mean, of course, if you have very strong redshifts, means that the light rays propagation time scale is very long. And for example, the gravitational wave echoes can also be delayed with respect to the observer, etc. So, but of course, we are also quite aware of the fact that when you have stable light rings, you have instability. But we are not sure whether this strong redshift effects can have some like the same postponement on the instability timescale. So that's why what we are curious about.
Yeah, so it's not clear. I don't have a good. That would be it would be very interesting to have an answer to that question. I think I understand, but I'm afraid it's still an open problem.
Yeah.
Well,
Thank you very much.
if you are able to give an answer, please let me know. I would very much like to know.
Thank you very much. Yeah.
Hilarious.
Thank you for the very nice talk. I actually have two
Thank you.
questions. The first one is whether light rings have been investigated for dynamical spherically symmetric spacetime, like for example in the context of gravitational collapse.
Well, I think there's some in spherical symmetry, you say. Um, so I think that there are some work. So spherical symmetry, but with collapse. I think there. I don't. I don't want to not properly cite. I think there's some work with Volker Perlich, I think, but I'm afraid don't. I think with someone else. I'm afraid I don't recall the name of the other authors. But if you
Okay.
want, please send me an email and I will reply with the references that I have. But there is some work on that.
Okay, and also about the back reaction.
No, on the back reaction, no, no. In that case, I think is just it's a toy model. It's not you don't have a full. I wouldn't say you don't have a kind of a full back reaction of an equilibrium spacetime. You need to start with an equilibrium spacetime and not with a spacetime that is initially collapsing already. You see? So the point is you can construct a lot of models that have stable light rings that are unstable, that you can expect them to be unstable for different reasons, and or start with a configuration that is already not in equilibrium, which kind of defeats the purpose. But well,
Okay.
I hope I've partially addressed your question, your first question, I think.
Yes, and regarding the second question, it's more related to the first part of your talk, and especially to the theorems you mentioned
Hmm.
that you expect a stationary axisymmetric black hole spacetime to only have standard light rings. But I think the proof that you mentioned, the topological proof, uses the assumption of circularity.
It
So I was
does.
wondering whether what happens if you relax this assumption? Can you
Mm,
still investigate the fate of light rings?
yeah. So let me go back. So slides, just so that we are clear. I think it was, yeah, I think it was this result that you are mentioning, right? So in that case, I did mention, although it's not written here, I think I mentioned circularity is one of the assumptions, and it's a critical one indeed. And although it's not completely clear to me what changes, I suspect I have actually exchanged an emails with Volker Perlich about this, and I think he suggests. So let me say it in this way: this paper uses an effective potential from which to define a gradient and then associated topological charge. And the thing is that this potential assumes, or it is constructed assuming circularity. So if you don't have circularity, well, it's unclear what's the sort of framework that you need to use. And after some email exchanges with Volker Perlich, I think he suggested some sort of potential that circumvents this problem, from my understanding. So I think there is a way to generalize this result without circularity, although this was until very recently an open problem. But let me emphasize that this has not been kind of made very concrete. I, yeah, I think that is what I have to say for the moment.
Okay. Yeah, I would be interested in knowing more about this.
Okay.
Any other questions? If not, maybe I can ask one. Do you know any effect which it has maybe on gravitational lensing? Are there additional features which may occur, or
Or the stable. Well,
yes?
when you have an horizonless object that has a light ring, so you have these light rings in pairs if they are degenerate. The unstable light ring creates a very sharp kind of multiple images features that, like, you have. It's not the edge of a shadow, but you get also a hierarchy of multiple images, but without the shadow. The stable light ring doesn't have such a sharp feature. I think that goes along the flavor of your question. what we observe in some cases where the potential well is very deep, so the potential well of this light ring potential, is that it might induce some chaoticity in the orbits. But yeah, but this is a very heuristic perspective, and in some cases it doesn't really apply, namely in spherical symmetry. It's not. I don't have a very good answer to give you, honestly. So the stable light ring is there, but it's not doesn't give a very sharp image feature, I'm afraid.
Thank you.
What can happen is that you can have, for example, different families of generalization of these light rings, which in some contexts is fundamental photon orbits and so on, which is essentially orbits that have that are kind of bounded in a very similar way to these light rings. And when you have these stable light rings, you can have a very interesting interplay between these families, and you can have a jump. So you can have this kind of very sharp edge that would have the shadow, and then you can have a discontinuity in somewhat in the family that gives these lensing features. And that can happen precisely because you have these kind of stable orbits. So you see an effect indirectly in some way. But well, that is the best I can give you, I'm afraid.
Thank you.
Okay,
Other
thanks.
questions? If not, I suggest we end the official part of the seminar here. Jay, could you stop the recording?